Recording live from the ARC studios, welcome to the Sustainability Podcast. Our goal is to provide engaging discussions on a broad range of topics regarding cybersecurity, sustainability, supply chain management, plus much more. For more information and to get into contact with us, visit us at arcweb.com.
Podcast. Today, I'm thrilled to be joined by a senior leader of ARC Advisory Group, my colleague, Ralph Rio. Ralph, how are you today?
Very good. Very good. I'm delighted to be able to do this podcast with you, too.
Ralph, you've had a long and varied career here at ARC. Perhaps you want to touch on a little bit of that, but more importantly, what are your current areas of research?
So my current areas of research are around engineering design software and building information modeling, EDS, BIM, and digital twins. So that is my current focus at ARC Advisor Group.
So for the audience at large who may not be familiar with those acronyms and those technologies, can you go slowly through each one of those?
Yeah, so this is software to design both plants, so it's mostly in the continuous process industries. Also infrastructure, I'm talking about civil engineering like bridges and highways, and then buildings. So it covers engineering software to design those kinds of assets.
So I see three types of infrastructure: plants, factories, manufacturing facilities, things like that, roads, and more civil infrastructure, let's call it, and then buildings.
Yes.
Now, you mentioned a number of software acronyms. Which of those apply to which of those applications?
So engineering design software is used across all three types of assets. BIM, building information modeling, is specific to buildings and is more specific to the engineering data and documents associated with the building.
Is there an analog of BIM for the other two applications?
Well, the engineering design software also keeps track of data and documentations for engineering. And they, of course, also have capabilities to design the physical plant or the bridge and building. Usually they involve some simulation to make sure these things can take the stresses, and also very specific functions around the electrical piping and those kinds of utilities.
So before I'm ready to jump in and ask you about challenges to the industry, but what problems does software like this address? Why would you use software? And well, in the old days, why would you not do it by hand?
Yeah. Well, these days, I don't know how you would design any of those economically. How did you design those things by hand? When I was in school, I did have put pencil and paper and used a protractor, etc., to do some drafting. But
and a slide rule.
Yeah, we cannot afford rooms filled with draftsmen like we used to have decades ago. The software not only creates the documentation, but it includes functions that allow for the rapid design of a building, like I mentioned before, the piping and the electrical. So there are specific software functions that lay out those piping and electrical very efficiently. So in a nutshell, it's a huge improvement in engineering productivity compared with attempting to do it manually, and error correction, because although the simulation and of the stresses, so you know that this structure is viable and sustainable, and even after some corrosion may occur or an accident of some type, will still stay in place.
So it's not just structural analysis, it's also architecting where each of these components goes. And in fact, I could imagine in a complex road, you might want to know is some electrical conduit attempting to occupy the same space as the stormwater drainage or things like that.
Yeah. So, roads look very simple because when we drive on them, all we see is the pavement on top, right? But roads are actually very complex because there are several layers going underneath the road of different types of materials. There is also some soil analysis that has to occur to know whether or not the road will stay in place, won't sink. Also, you need to understand water and water flows around the road so it doesn't get washed out. And then, as you know, the road has lines on it. It has off ramps. It has guardrails, all those kinds of things, lighting in some cases. All that needs to be engineered and documented, and is done that in the software. So, and these things vary by distance. So, at mile zero of a highway, you have one set of parameters. A mile down the road, there may be something different about the land, the soil, the grade, etc. And that all needs to be designed and worked out. So a road is what they call a linear asset, meaning that you need to understand it and its maintenance by sections of the road.
Yeah, and in fact, I was surprised that you neglected to mention that the right-of-way of a road often carries communications infrastructure, fiber cabling, telecom equipment, could be natural gas pipelines, could be an awful lot of other assets that are not just you and your car on the road.
Agree. Yeah.
So that's fascinating.
So
What?
that reinforces how complex a road is beyond our normal understanding of just a pavement on top.
No, exactly. What complications, for those of us who are not all that familiar with plant design, what similar situations happen in the world of plant design?
Well, that starts out with designing the process. What process steps are going to occur and what happens in each one of those process steps. That's normally called the front end engineering design. And then that feeds into the design of the plant. Now you start designing each one of those process steps, where they're physically going to be located, the pipes that go in between them. If you look at a refinery, for example, I've read that there often is somewhere around 40,000 pipes inside a refinery, and 10,000 or so or plus pumps and valves. It is extremely complex, and all that needs to be laid out and designed.
Yeah, I was trying to think of the equivalent to that communications infrastructure on a road, and not all plant facilities are simply machine tools on a concrete slab covered by a building.
Yeah, that's over in the
that's in the
discrete industries, and that is considered a building and is part of BIM.
Okay.
All right. When we talk about plant design, we're really talking about the continuous process industries, which is like bulk chemical, refinery, and
Pharmaceuticals.
those kinds of industries.
Fascinating. So in the world of buildings, while it's not formally a plant according to your definition, there are some special requirements I can imagine for certain manufacturing buildings like semiconductor fabs, or or others in terms of air quality, or other parameters that can be managed much better by sophisticated software tools.
Yeah, so surprisingly, semiconductor, there's only about 200 semiconductor plants in the world. So that is kind of even though each one of them is nowadays it costs somewhere around $10 billion a piece. That is, from a software design viewpoint, a fairly small market segment. So I'll get away from that and talk more about the continuous process plants, which are very, very different than a road or a building. A building, I'm thinking of a commercial building, could be a hotel, could be an office building, and this also includes the buildings that are in an airport, for example. They are, compared to a plant or even a road, they are much simpler in that you do have utilities, but the level of complexity is at a lower level.
Got it. So we didn't touch on BIM all that much. What are the what really are the specific features of a BIM as opposed to more as to the other software tools?
Yeah, so the other software get much more in functions that are used for design, like generating where the piping should go, the best route, looking at alternatives and choosing the best route, for example. That's an example of how AI has started to penetrate these applications. The BIM is just focused on the documentation and engineering design data. So you would use software, engineering design software, to really architect and design the building. That would be separate from BIM.
Got it. Now, to further complicate our discussion today, you had mentioned a digital twin. What is a digital
I've
twin,
heard of that,
and where does that relate in our conversation today?
Well, in the design area, digital twins exist for all three types of assets: plants, infrastructure, and buildings. And they are, in the design and build part of the project, they are used to make sure that everybody has the same data, the most current version of the data and documentation. And this prevents rework. For example, in the case of a plant, before digital twins, and this is an amazing number, roughly 30% of the work was rework. So that's labor. About 12% of the cost was rework. That includes materials of a plant. So when you have rework, that causes a delay, increase in cost, and the project is less likely to get delivered on time and within budget. So digital twins, by sharing this information effectively, provides a means to reduce or eliminate that rework. That's the documentation side of a digital twin. A digital twin also contains a 3D model, so that, and I start to call this the new user interface, the next generation user interface, where people will navigate to an asset, double click on it, and get information about that asset. So in the case of a 3D model, it provides situational awareness. So, a simple example is when someone goes over to do something, do they need to bring a ladder type of thing? What else could they do in that area? If they're next to a particular pump, there are other things they can do in that area while they're there, and a host of other kinds of use cases. And then the third function of a digital twin is the simulation. So that you can assess and make designs, do what if analysis to provide the most optimal design for that plant, infrastructure, or building.
All right, so we've discussed engineering design software, BIM, and digital twins.
Yes.
Can you describe? I mean, you touched on it anecdotally, but where do each of those reside in the product life cycle, in the installation life cycle? Meaning,
well,
go ahead.
Yeah, we've been talking about engineering design software, and that software is used to design an asset. So we're talking about the design and build. That software usually also includes construction management. Most software providers provide something to manage the construction of the project. So it's all in the design and build. There's a whole another set of software applications that are used after it's built, after handover, to operate and maintain it. And there's a set of software applications for plants, and there's a different set of software applications for buildings, and a third set of software applications for infrastructure. Those
Ralph,
applications are not part of the study.
it was a bit of a leading question because digital twins can be used across the entire asset lifecycle, correct?
Well, the digital twin created for design and build and that's where they're all created, by the way, during design and build to manage a project. That is optimized for the business processes for design and build. After handover, for operate and maintain, there's a whole different set of business processes. And one of the problems right now that the industries are dealing with is how do you sustain that digital twin? A lot of digital twins, unfortunately, die after handover. And there are many people, the focus of which are working with ARC Advisory Group, are working with suppliers to figure out how to modify their software to support the business processes and operate and maintain.
That's interesting. So can I infer there that I may need a completely different digital twin at runtime after delivery, after commissioning?
Right now, many people are creating completely different digital twins. We see this particularly for oil platforms because the use case is so strong. You want to minimize what you do on the number of people that are on an oil platform. Sure. So you try to do as much as possible using a digital twin before anybody has to go on the platform. And this is all around operate and maintain. So yes, digital twins are used in operate and maintain that are independent and different. Some suppliers have had success enabling their digital twin to make it through handover and into operate and maintain. And there are some examples where that has been successful. We just need much broader adoption of those capabilities so these digital twins continue and operate and maintain.
It's interesting to me, Ralph, I've done quite a bit of work in systems engineering, and I'm struck by the fact that, while it does cost a little bit more upfront the cataloging the user needs over the entire project lifecycle might be valuable, so that you could create a digital twin that would make it from project conception all the way to retirement. But that costs up front.
Yeah, most people would agree with you, nearly everybody, except for the suppliers of that unique digital twin just for operate and maintain.
There you go.
Yeah, you're right. And the industry is moving in that direction fairly rapidly.
That's great. Ralph, this has been a fascinating introduction in 21 minutes. Let me move on to somewhat my standard set of questions, which is so what really are the challenges of the industry at this point?
Well, the primary challenge is there aren't enough engineers. In the U.S., we graduate about 60,000 engineers per year, but far more are needed than that. Easily 100,000 new engineers are needed every year in the U.S. We only graduate 60,000. And Europe has a similar problem. So the primary driver for outsourcing to engineering firms in India is that they don't have enough engineers in Europe and the U.S. I've heard this multiple times from end users who are contracting with the India engineering outsourcing firms. India, by the way, graduates roughly 500,000 engineers a year. It's a much bigger country, a lot more people, but it's 500,000 engineers a year. And a lot of them are employed in the global engineering services companies. People like L&T Technology Services, TCS, Tata Consultancy Services, and Infosys are key examples, but there are many more beyond that.
So typically I would ask the follow-up of how do we surmount those challenges? So is it simply outsourcing?
Well, that is the solution that has been working. The other solution that the software providers are doing is to focus on engineering productivity, do more with existing staff. And we see artificial intelligence being rapidly picked up by the software suppliers and added to their applications. So it is not something that operates outside the application, but it is embedded functions within via dialog boxes, et cetera, within the applications. I saw a demo once, it just surprised the heck out of me. It was in an application. The engineer needed to design a bracket. What the engineer did in the software is to select the two surfaces that had to be joined, and then clicked a button, and the software automatically designed the bracket. And you could choose if you wanted to use traditional fabrication methods, i.e. metal removal or stamping or casting, or if you wanted to use additive manufacturing, 3D printing. And they could go either way. If you needed a lot of brackets, you'd probably go with the traditional way. But if you're doing something like a landing gear on an airplane, you probably would go with 3D printing. But it automatically, before your eyes, in seconds, created the bracket. So it's those kinds of engineering productivity issues that are the focus of a lot of the engineering design software suppliers.
I could see that because we know that even ChatGPT today is writing an awful lot of software code, for example.
Yes.
Try asking it to write some Python, and there it is.
Yeah.
Certainly.
Now there's another thing going on. I think that's a primary one. There's another thing going on that for construction, to improve construction management, they are fabricating more materials and components off-site. So rather than cutting a pipe to length on-site, they cut it to length off-site, and they may even add the endpoints, the the name escapes you off the
Plans or
top of my
whatever.
head.
Yeah.
Yeah. So now with 3D laser scanning, they get the accuracy of the existing conditions so they can do that stuff off site.
Right.
And now construction is starting to look more like an assembly operation than it is a fabrication operation. And that is that lowers costs, improves quality, and speeds the time to completion.
That's fascinating.
And of course, the third one is digital twins, but we already talked about that.
Right, we
We'll
did.
revisit that again.
So Ralph, what do you see for the future?
Well, I see the future moving to higher degrees of automation of the design process through those three things that I just mentioned: productivity with AI, construction management by fabricating things off-site, and digital twins.
Beautiful. We've covered a lot of ground in half an hour. Ralph, do you have any last comments for our audience today?
Yeah. Encourage your children, your nieces, nephews, or anybody else about ready to go to college to get an engineering degree. We desperately need engineers. And by the way, I read a report that the average engineer makes twice what a Bachelor of Arts do during the course of their career. So not only is it much easier to be employed, it's much more lucrative. Encourage the young ones to become engineers.
From one engineer to another, that's a good thought.
Well, think about it for a moment. Look around you, where you're seated right now. Everything is engineered. The PC you're looking at, or the phone that you look at your desk. Somebody had to draw that, the dimensions. Your house, some architect had to design your house. You could go on and on and on. Everything you see in modern society was designed by an engineer. And to see, from an engineering perspective, to see your design become reality is tremendously fulfilling.
It certainly is. Well, again, our guest today has been Ralph Rio of ARC Advisory Group. Ralph, this has been a fun half an hour. Thank you very much for your time. And we look forward to seeing our audience again on another episode of the Sustainability Podcast. Thank you very much.